Hi, my name is Rodrigo Hernangomez. I'm a research associate at the Fraunhofer Heinrich Hertz Institute for Telecommunications, HHI for short. And here I'm also pursuing my PhD with the Technical University of Berlin. This video is a presentation of our paper, Online Quality of Service Estimation for Vehicular Radio Environments, which is also part of the conference program at EUSIPCO 2022. I hope you like it. The first thing to say about this work is that it was supported by the German Ministry of Education and Research as part of the AI for Mobile project. The research interest of this project are artificial intelligence methods in the context of wireless systems for mobility in industry and traffic. To this aim, AI for Mobile brings together several industry and research partners. In fact, this specific work is the result of a collaboration of HHI, represented by Martin Kasparick, Noor, Sławomir Stańczak and myself, and Alexandros, Palaios and Gayathri Guruvayoorappan from Ericsson Research. Let us take a look at the outline. I will start with a brief introduction to motivate the importance of quality of service, QoS for short, in vehicular wireless networks. After that, I will go on with a description of the measurement campaign that was carried out within AI for Mobile and that provides us with a decent dataset to explore QoS estimation. After a discussion on our experiments in this regard and an evaluation of the obtained results, I will finally wrap the presentation up with a conclusion. About QoS estimation in wireless networks, it is not difficult to see why vendors are interested in it, especially if it is carried out in their infrastructure to provide a better service to end users. Now, the trend of machine learning for estimation has also reached the area, and it comes as no surprise that researchers have been doing quite some work to apply machine learning to QoS estimation. Now, one may wonder what this has to do with vehicles. You may call us dreamy, but when we started this AI for Mobile project, we envisioned quite some use cases where QoS estimation and prediction is vital for cars, especially if they are connected to the internet and if they are self-driven. Okay, the self-driven part is not really there yet, sure, and it is a long way until this comes, if it comes. But precisely because of this, it is sensible to think of a transition phase where cars will be able to drive autonomously while they still ask for human help in complex situations where they cannot handle. Then one option to keep the autonomous experience for the passengers is that a teleoperator takes over the control of the car through an internet link until the road is safe again for self-driving. In this situation, and since the internet link becomes a critical resource, we want to be able to predict the QoS along the way and use these predictions to plan a route that guarantees enough quality for teleoperated driving. Back to machine learning, one has to acknowledge that automotive scenarios pose a challenge to the ML framework. Indeed, the radio environment will drastically change as a vehicle traverses different road scenarios. This will typically cause a drift in the data distribution, which often degrades the performance of ML algorithms if they do not account for it. Luckily, there is an extensive literature on online and adaptive algorithms that address this problem, and we have tried to investigate it for the QoS estimation setup in this automotive scenario. Before we dive into algorithm specifics though, it makes sense to first take a look at the data we have worked with. Together with other AI for Mobile colleagues from BMW and Dresden, we carried out a measurement campaign collecting mobile data for a week with 12 devices while driving 4 cars along the A9 highway close to Nuremberg, South Germany. We chose those surroundings of the A9 highway for 2 main reasons. One, the different radio environments at hand, and the mobility testbed from the 5G Connected Mobility initiative that Ericsson operated there as the second reason. The relevant radio environments for us are highlighted in the map. You can note from the red frame that we, of course, drove along the highway with speeds above 120 km per hour. But we also took some measurements in the nearby suburban town of Feucht at 30 km per hour, highlighted in blue, and we even took some detours through a couple of rural pathways in green. We used these different environments as a basis to study distribution drifts when a vehicle travels from one environment to the next one. The benefits of Ericsson's testbed in the area become evident when discussing the type of data we were able to collect. Not only the basic physical layer information from LTE, such as signal-to-noise ratio, which is easily available for the end users, but also information on the base station side, such as the total throughput in the cell and the number of connected devices. On top of that, we benchmarked the obtained throughput, which we have considered as our QoS metric, and the ground truth to train our algorithms, while we have kept the remaining 7 values as input features. Overall, our joint effort managed to obtain a unique dataset that is richer than the ones typically used in literature, and you can check it out in the references later. Now we are in the position to talk about QoS estimation. We have formulated the problem as a regression, that is, we use our 7 features as x, or the input to our estimator, and we try to fit it to produce an output y that is a real value and it is close to our ground truth, which again is the obtained throughput. For the algorithm, we use an ensemble of regression trees, also known as random forest. The main concept of a regression tree is sketched in the right diagram, where a basic decision in the form of inequality tests on particular features is taken through the nodes of a binary tree from the root to the leaves, and the destination leaf then estimates the real output t of x as a distinct affine combination of features. Finally, the output of several different trees is aggregated to produce a low variance estimation y hat. While I will not go into the specifics of training algorithms of random forests, I'd like to hint at the use of the so-called standard deviation reduction method to find the decision rules on each tree's node. Random forests are great estimators, but their performance is typically bound to independent and identically distributed data drawn from a static probability distribution P. Mathematically speaking, the distribution drift setup poses a probability distribution that changes over time, hence the subscript I on P, and P sub I is allowed to take different forms for different values of I. A good way to tackle such naughty drifting distributions are online algorithms. For the case of tree ensembles, Gomez et al. Have developed a method called adaptive random forests that works in the following way for our setup. Imagine we have a vehicle in our suburban area that is connected to a base station. The propagation environment in this suburban area makes the signal-to-noise ratio obey such a probability distribution as you can find on the bottom right part. The base station will collect some mobile data from the vehicle and will issue a QoS estimate based on a random forest. Let us assume that this random forest has been pre-trained with data from the same suburban environment, where the vehicle had already dwelt for a while. The actual QoS will be available with some delay, but since we are in a favorable situation, the estimate y hat will be close enough, and the base station will just use y to train its regression trees for the future, and also its background trees. The purpose of these will be clear in a minute, bear with me. Now, imagine that the vehicle moves away of the suburban area, but not so much that the propagation characteristics completely change. In that case, a new y hat and y appear, and the random forest keeps training. Now, because the data distribution has changed, some tree t in the ensemble may not be fit for the data anymore. In that case, a change detection method C with a certain threshold, delta sub w, issues a warning. This will place a new tree in the background pool, which will start to be trained. Think of background trees as substitutes in a soccer match ready to jump to action whenever a player on the field becomes exhausted. Training will resume for all remaining regression at background trees, including the newly created one. Eventually, the car will drive farther away into the highway, and the data distribution will have nothing else in common with the suburban PDF. If we now cycle through our routine again, a drift will be detected during training. In this case, a higher threshold, delta sub d, is issued. This triggers a substitution in our ensemble. The faulty tree goes off the field, and our fresh background tree comes to the foreground after some hard work training. Then the process goes on indefinitely. Now it is time to discuss whether this algorithm actually works. For this, we have taken the suburban and highway data from 4 devices and run experiments on random forests with and without the adaptive algorithm I have just explained. We also performed experiments for a single device, but we did not find significant differences with respect to the multi-device setting. For the normal offline random forest, we just trained it with the suburban environment and evaluated with both suburban and highway data separately. A typical performance example is shown in the upper plots. The random forest here is able to learn the suburban radio environment, which one can notice since the estimations y hat on the left plot are close to the ground truth y, that is, the data is concentrated on the plot's diagonal. For the highway distribution on the right, though, the model estimation quality considerably drops as a strong skew appears at the high end over 40 megabit per second. For ARF, we also perform offline pre-training with the suburban data, but we then let the adaptive training algorithm run on highway data. A look at the bottom right plot highlights the effect of the adaptive approach. The algorithm can incorporate new information to the model, and thus it behaves better than offline RF in the high throughput regime. As a final comment on this slide, the left table shows the median error across different choices for the change detection method in relation to the median throughput in our dataset. The numbers confirm the observed trend on the plots, where the offline random forests overfit for the suburban environment and thus incur an error of almost 42% in the highway environment. ARF, on the other hand, provides a balanced performance both when the devices stay in the training environment and when they enter a new one. Let us also take a closer look at the effect of the change detection method Z. Here we consider 4 alternative options: adaptive window, ADWIN, Kolmogorov-Smirnov window, KSWIN, Höfting-based drift detection method, HDDMA, and the Page-Hinckley test, PHT. The respective references can be found in the plot legend. For each method, we throw out different threshold values, which are proportional to the marker sizes of the scattered plots. What we try to investigate here is the sensitivity of the different methods, measured on the horizontal axis as the percentage of data points that trigger a data drift, in relation to the accuracy on the vertical axis, measured as the error over the median throughput, same as in the table of the previous slide. One aspect that may call your attention is the poorer performance of KSWIN in green on the left plot, which could indicate that this method fails to identify the parts of our data where drifts occur. Other than that, we cannot observe that the performance of ARF is severely affected by the number of detected drifts, which lies below 5% for all methods except HDDMA anyway. In the event of equal performance, the obvious goal would be to minimize drift detections to reduce retraining and thus boost computation and energy efficiency. In summary, thanks to this work, we can conclude that online learning in general and adaptive random forests in particular are suitable for QoS estimation in the face of changing wireless environments with distribution drifts. Indeed, online learning reacts to drops in the wireless performance, which can reduce the overhead of offline revalidation and retraining on constantly increasing datasets. The price to pay is the fine-tuning of the change detection method Z in relation to the expected data, since drift detection is the key ingredient of ARF. As a final look into the future, there is a common understanding among the partners of this work that data governance is a serious issue whenever the use of users' data is involved. As such, we would like to investigate how machine and federated learning can enhance privacy of shared information across critical infrastructure. Please let me present some selected references that we have used throughout this work. You may want to pause the video and note them at your convenience. Thank you for watching this video presentation. I hope we can meet soon in person at EUSIPCO or any other conference. Until then, do not hesitate to reach out to me with any questions or inquiries about our work. Goodbye.